that I will be talking about today is something very general, something new. Astronomy is the oldest science, and it also is one of, why people do astronomy is not just because they are there, but it's also a human quest, in some sense, to find our place in the entire universe. And I think that's, no matter what you are, whether you are a scientist, whether you are a Formula One racing driver, or whether you are a student, whatever you are, I think at the very deep down level of our hearts, we really want to know where we belong in the universe. So that, I think, is the background that I will briefly touch upon, what people have been doing. And then something new, something which is basically coming up in India, and something called LIGO India. And this is a new experiment, and this is going to completely change the way we look at the universe. And that's why I kind of tried to put a rather provocative title here, tuning into the symphony of black holes. Of course, black holes, it's not an orchestra. So what do you mean when you say tuning into the symphony of black holes? What I mean by that is, black holes emit a certain kind of radiation which was predicted in Albert Einstein's theory. And these radiations are gravitational radiations. And you'll see what exactly I mean. And there is a worldwide effort since the last 10 years to actually detect these gravitational wave radiations in flesh. And that will give you completely orthogonal information about how the universe is and how it works. And there's a lot of work that I will point out towards the end of my presentation, both at IIT Gandhinagar as well as at our partner institutes all over India and the world. And if you are a student and would like to come to us and figure out how you can participate in some of these things, you are most welcome. To begin with, let's set the stage first. So here is a very gorgeous picture of a blue-green Earth. And what this does for you is to emphasize the uniqueness of your existence. You think that, well, we are special. We are special. Okay? We have iPhones. And then this is a picture taken by the Voyager spacecraft. This is a spacecraft which has probably gone on to this is one of the man-made instruments which was actually sent out to investigate the rings of Saturn and also Jupiter. And now it has crossed the solar system, and I think this is the farthest we have been able to send out something that was made by man. And when this guy turned on to Earth and took a picture of the Earth, you found that, well, it's hardly visible here. You, me, everyone else, we are right here. This little blue speck that you see here. So, Carl Sagan, I don't know how many of you have watched Cosmos. Have you watched this program called Cosmos by Carl Sagan? Yeah, that's very good. So, he says that you are, he put it very well when he saw this picture of the Earth. He says that you're nowhere in astronomical terms. It's very humbling. When you see this picture, you find that you're basically a speck. As far as the enormity of this cosmos, in the cosmic scale of things, you are basically a point, a speck. So this is the stage, and yet, what stands out about the speck is our willingness to learn about this entire universe in many different ways. And today what I'll try to show you is a new way in which we're trying to, a new window that we're trying to open up into the universe and see for ourselves how does the universe look in gravitational waves of the creation of the universe. And that's what we want to begin. But of course, there leaves this very big question mark here that maybe other sources that we have not even thought about. Remember, whenever you observe the universe in a new way, you always find new things which we had never even imagined would exist. And therefore, I mean, I've put up this slide with this big question mark, saying that there may be things that just go bump in the night, which may, create gravitational waves. How might you detect gravitational waves? Now that is the thing that we're warming up to something more concrete here. It's very, very difficult to detect gravitational waves. And the reason is because they interact very, very weakly with matter. For instance, if I had a detector to see Jupiter, sometimes, have you seen Jupiter by any chance? I mean, on, say, night sky? You have. So, the strongest sources of gravitational waves will be as bright as Jupiter if you talk about the amount of energy that is coming on the Earth. Yet, they interact so weakly with matter that these would create changes in distances of the size of 1,000th of a nucleus dimension. How big is the nucleus? Does anybody know how big a nucleus is? 10 to the minus 15. 10 to the minus 15. We are talking about 1,000th time, 1,000th part of that. And these are the strongest sources of gravitational waves. So, I'll just tell you a little bit about how we plan to detect these gravitational waves. These gravitational waves are detected using a technology called laser interference. And I'll very briefly tell you how this thing works. See, what you have is a mirror and a laser. The laser shines a light at this mirror, which splits it into two parts at right angles. Now these go, and these are again mirrors. They go to these mirrors, they reflect back. Light from this part also does the same, comes back to this point. And then they interfere. They create interference patterns. Create patterns which tell you how long these slow down, how long these are. When gravitational wave comes and hits these mirrors, what happens is, alternatively, these arms stretch and gets pushed. So what happens is the focal length varies as a function of time. And hence, the light's phase changes as a function of time. And when they come and interfere here, they create an interference fringe, like alternate light in dark patches, which change with time. Of course, this can also change with time if these guys were shaking because of noise. That makes it so hard. How do you separate the change in length due to some astrophysical force from something that is shaking the earth? These are so sensitive. For instance, in one of the sites, there is a logging facility. So they are felling the trees, paid cut. So the noise creates sufficient signal to be actually detected. Let me show you the real facilities here. So this is the real picture of one of the observatories. These are the two 4-kilometer arms. And this is the central facility where the laser is injected into the system and so on. But these are not the only type of detectors. There are other kind of detectors. They are called bar detectors. Bar detector is nothing but a single piece of aluminum. And if the gravitational wave comes and hits that piece of aluminum, it's like hitting a piece of bell. Bell hota hai? If you hit that bell, what happens is it dissipates its energy depending on what is called the quality factor of the bell. So these are bars which have very high quality factor. So once you hit it, the energy is dissipated over a very long time. So if you observe the bar for a long time, you can build up your signal to noise ratio and hence detect the presence of gravitational waves. I'll tell you a little bit about the Indian efforts that are going on. So here is a picture which shows you where these gravitational wave detectors are currently in operation. There are two of them called the LIGO detectors at two extreme ends of the United States. A similar detector is there on the Italian-France border called the Virgo detector. And there's one in Germany called Geo detector, but which is not as big as the other detectors. There are plans of building a similar detector in India, and that's what we mean. Initially it was called Indigo, but now the name has changed. It will probably be called LIGO India at some point, if it gets built. So right now we are proposing to the government. These are extremely expensive machines to build and operate. But these detectors are very unique in the sense that it's not like a telescope. It's not like if you have a very big telescope, you can do cutting-edge science. These detectors only work well when they work as a network. So therefore, if you build one, it's not, the aim is to join the others and make a network of detectors. And this network of detector is much more sensitive than any single network, any single detector that is a part of this network. For instance, one advantage I'll show you of having this network of detectors in India is that suppose I want to locate a source using two detectors. You find that the source is like kind of spread out all over the sky. As soon as I put in a new detector, you find that the same source, you can localize that source, you can find out where that source is very, very easily. So these are the participating institutes in India which are participating in this probably the biggest scientific experimental science experiments that are being built in this country. And right now we have, this list is a bit dated. Okay? More institutes have joined, and you can see that new institutes are coming up on board all the time. And currently we have 41 institutes which are part of this a consortium called Indigo. And the business of Indigo is to join hands with all the other network, all the other detectors in the network, and basically detect gravitation.